Hey everyone, and welcome. Today, we're going to crack the case on a really powerful algorithm that honestly acts like a master detective for any kind of network. It's called the Floyd-Warshall algorithm, and it is the ultimate tool for figuring out complex systems. So, what kind of massive puzzle are we trying to solve today?
Well, imagine you're running a massive global delivery service. You don't just need the best route from one warehouse to one city. No. You need the absolute fastest route from every single warehouse to every single city, all figured out at the same time. This is what's known as the all pairs shortest path problem. And yeah, it's a huge puzzle. Where do you even start?
And for a case this complex, you call in a specialist. Enter the Floyd-Warshall algorithm, our master detective, purpose-built for finding every single shortest path in a network.
Okay, let's look at the official file on this guy. The key phrase you got to notice here is dynamic programming. Now, don't let that term scare you. It's just a really clever way of saying that instead of trying to solve the whole giant problem in one go, the algorithm breaks it down. It solves all the little easy sub-problems first, and then it uses those answers to build up to the final complete solution. It's smart, not just strong.
Now, what makes this detective so special is its versatility. It handles positive weights, like distances or costs, no problem. But its real superpower, it can handle negative weights. Think of those as rewards or shortcuts in your network. The only thing it can't deal with is something called a negative weight cycle. And that's basically an infinite money cheat code, a loop that lets you get a better and better score the more you travel it, which would break the whole idea of a shortest path. So it wisely stays away from those.
So how does it actually work? You might be expecting some crazy, complicated formula. But the entire logic, the whole genius of it, is built around one surprisingly simple question about taking a smarter detour.
At every single step, for every pair of points, the algorithm just asks this. Okay, is the direct path I currently know from point I to point J the best I can do? Or could I actually get there faster if I made a little stopover at some other point, let's call it K, along the way? That's it. That's the entire investigative strategy right there.
And this right here, this is the detective's secret weapon. This one line of code is just the math version of that exact question we just asked. It just says, hey, the new shortest distance between I and J is whichever is smaller. The old distance I already know, or the distance it takes to go from I to our stopover K, plus the distance from K on to J. It checks the detour, compares it, and always keeps the shorter one.
All right, enough theory. Let's actually watch this detective in action. We're going to track the whole investigation using what's called a distance matrix. Just think of it like the detective's case file, and we're about to watch as it gets filled in with clues.
So this is our crime scene at the very beginning. This matrix only shows the direct paths that we know about right now. The zeros down the diagonal just mean that going from a city to itself costs, well, 0. And all those INF symbols, that's just short for infinity, which is our code for we don't currently have a direct path between these two places.
And boom, our first big break in the case. We asked the question, can we find any shortcuts by using City 1 as a stopover? And the answer is yes. Take a look at the path from City 0 to City 2. It used to be infinity, but we now see that going from 0 to 1 costs 5, and going from 1 to 2 costs 3. Add them up, that's 8. And 8 is a heck of a lot better than infinity. So we update the map.
And the process just keeps on rolling. Next up, we check City 2 as a potential detour. And bam, 2 more new paths discovered. The path from 0 to 3 was 10, but now we know we can go from 0 to 2 for a cost of 8, and then from 2 to 3 for a cost of 1. That's a total of 9. A new shortest path. The same logic uncovers a new, shorter path from 1 to 3. The map just keeps getting better.
So, after methodically, patiently checking every single city as a potential stopover for every single pair of other cities, we get this, the final matrix. This is the solved puzzle. This table now contains the absolute, guaranteed shortest path between every single pair of cities on our map. The detective's work here is done. Case closed.
So our detective is clearly brilliant. But where does it fit in the grand scheme of things? In a lineup with other famous pathfinding algorithms. Knowing this is the key to knowing exactly which detective to call for which case.
First, we've got to talk about its signature move. It is incredibly thorough. Its time complexity is O of V cubed, or V cubed, where V is just the number of vertices, or cities. Now, what that really means is, if you double the number of cities in your map, the time it takes to solve could multiply by 8. So yeah, this thoroughness is its greatest strength, but it's also its main trade-off. For absolutely enormous maps, it can take a while.
And this table just makes it crystal clear. If you just need the fastest routes from one single starting point and you have no negative weights, Dijkstra's your guy. Super fast specialist. If you still have one starting point but you've got those tricky negative weights, you call in Bellman-Ford. But when you need the complete picture, the whole map, all routes between all points, well then Floyd Warshall is the only detective for that job.
So let's just recap the whole method. It really just boils down to 3 key steps. 1. You set up your initial map with only the direct connections you know about. 2. You systematically, one by one, check every single other point in the network as a potential shortcut. And 3. You're left with the final perfect matrix, the complete map of all the shortest paths. Simple as that.
And that's really it. That's the Floyd-Warshall algorithm. A beautifully simple idea that solves an incredibly complex and massive problem. And it kind of leaves us with one final big question. Now that you have a tool that can find the shortest path between everything and everything else, what complex real-world system would you want to map out first?